See, is my screen visible?
Yes, we can see your screen.
Okay. Okay, well, I guess I'll begin. Thank you very much for inviting me. It's a pleasure and an honor. So I want to tell you about geometry, entanglement, and causality in the scattering matrix. And I want to start on the idea of entanglement generally in scattering, which is something that goes back several years now. So let me first just tell you a little bit about the collaborators. So the original work that sort of motivated all of this was from 2018, and that was in collaboration with David Kaplan, Natalie Clow, and Martin Savage, where we just looked at the relevance of entanglement for few body physics, in particular for scattering, and really in trying to understand better some of the results of that original paper. My graduate student Roland Farrell and I developed this geometric theory of quantum mechanics and other sort of related things, which I'll tell you a little bit about. And I also worked a little bit with a student, Mira Varma, on some things, which I might have time to talk about a little bit in the end. So the outline of the talk will be as follows. I first want to give a little bit of a motivation, because the title just seems a little bit sort of disjoint, many things, very, very general. And after the motivation, I want to tell you about real physics, and that is the problem of baryon-baryon scattering, which can now be analyzed using lattice QCD, although there are many issues associated with those lattice QCD simulations. And the potential relevance of entanglement, quantum mechanical entanglement in scattering. And then I'll tell you about a measure of entanglement that is specific for scattering, for the S matrix, which we call the S matrix entanglement power. And really, in trying to understand what this means, this leads sort of somewhat naturally to a geometric theory of the S matrix, which is really what I want to tell you about, and will be the bulk of the talk. So I should say, please feel free to stop me at any point in the talk if something is unclear. Okay, so I'm just trying, for some reason I have, so I'm just going to get rid of that. Okay, here we are. Okay, so the question is, do measures of entanglement provide interesting new information about scattering processes? So when we study scattering in quantum mechanics, we get some potential, we have some physical system, and we solve the Schrodinger equation, and we just assume that all quantum entanglement, everything that quantum mechanics does, it does via the Schrodinger equation, and we get out some phase shift or some observable quantities that we compare it to experiment. And so an interesting question to ask is whether there are some measures of entanglement that we could formulate that would give us some new information about the scattering that doesn't just automatically come out of the Schrodinger equation. And a somewhat different way to ask the question, we can ask, can we learn something about few body interactions at low energies that is solely due to entanglement and may not be captured in effective field theory? And so this is a slightly different twist on the question. When we study scattering, in a very general sense, we use effective quantum field theories. And effective quantum field theories are based on expansions of an action, say, in local operators. And so locality in space-time is really a fundamental part of the way that we study scattering. And so you can ask the question, there's some aspect of entanglement that is really non-local and is not being captured in the effective field theory paradigm. So what about baryon scattering? So baryons are highly entangled, strongly coupled many-body quantum systems, and that's particularly true if we look at them at rather short distance scales, that is on distance scales that are of the order of the Compton wavelength of the baryon. We see that there's the interior is a swarming mess of quarks and gluons, and that has a tremendous amount of entanglement. And the only real tools that we have to study this rigorously is, are for instance, lattice gauge theory, where we can really get at the, at least in some cases, at the quantum entanglement. But here I'm going to focus on baryons at very low energy. So it's a first approximation. The baryons are just structuralist spin 1/2 fermions. So looking at the distance scales much larger than the Compton wavelength of the baryon. So nucleon scattering. So just expressing it diagrammatically here, at very low energies, so just above the threshold for scattering, at very low energies. So these are energies much less than the pion mass. Then the unitary S matrix is constrained by various general physical principles like Fermi statistics, spin, and isospin. And we can, in a certain basis, we can express the S matrix as this 4x4 matrix, which I'm giving here. There's a piece which is proportional to the 4x4 unit operator, and then there's a piece over here that really entangles the spins. It's a dot product of the spins of each of the baryons that are scattering, and the coefficients are functions of the phase shifts, of which there are two. We have two independent phase shifts depending on whether the spins are aligned or anti-aligned. So we have the 1s0 and the triplet S1 phase shifts, which I denote delta 0 and delta 1.
Silas, so
yes.
So here by nucleon scattering, you mean proton neutron scattering, or?
That's right. So here you can think of really having proton neutron scattering. So we have both the singlet and the triplet. And I've chosen a basis of the spin operators, which gives a 4x4 matrix. And I could have instead written it in terms of the Pauli operators for flavor, right, in the neutron proton space. But they're actually, it's just a choice of parameterization, which in the field theory is related by Fierce transformation. So anyway,
Okay.
so the answer to your question is, yeah, it's best to think here that we have a neutron and a proton, each of which have two spin states, and at very low energies, this is what the S matrix looks like. You know, as we go up in energy, we know that we get new invariants, right? We get the tensor force, right, which would couple the spin matrices to the momentum, and then we have spin orbit coupling and lots of other things as we increase the energy.
Okay.
So how do we get this? Well, this is sort of a general form just based on general physical principles. The phase shifts are just some arbitrary functions of momentum. And when we go to calculate it, well, we can think of it in terms of effective field theory. I seem to be stuck at the moment. Let me see. Are you still there?
Yes, we can see your screen.
Yeah, for some reason, it's not, I'm just gonna have to, yeah, I'm just gonna have to restart that share. I just froze. Maybe it was just, I was just too long on one. Here we are. Okay.
Oh, we can see the screen.
Okay, great. Okay, so to calculate that S matrix, then for a specific theory or effective theory, then we have to write down an action, And in effective field theory, we write down the action to a given order, and we can then extract the potential. So in this way of looking at the scattering amplitude T, we get by taking the potential, which we get from the action, which for this case would just be a leading order. So having operators that don't have no momentum dependence, which would be a good approximation for very low momentum. Then the T matrix we just get by iterating the potential to all orders. And then from there, we get the S matrix by just adding the unit operator. And then you can just check that you just recover the form that we had for the S matrix on the previous slide, except now the phase shift is just entirely given in terms of the scattering lengths, which matches onto or the scattering lengths, I should say, for the two channels that match onto CS and CT. Okay, it's just again freezing. I cannot move. Okay. I don't know why it's just not allowing me to proceed. Okay, here we are. So then why work with the S matrix instead of the T matrix, the scattering amplitude? Well, as we'll see, we really want to have a unitary operator that characterizes the interaction. And the S matrix is a good candidate unitary operator. And also the S matrix is in some sense the most fundamental object for discussing entanglement for reasons that we'll see. Now, if we go back then to the effective field theory description in terms of these CS and CT operator, then the theory is very singular, and so we have to renormalize the theory. They're delta function interactions in coordinate space, and we can use dimensional regularization to do that. And so that's what I've used a dimensional regularization scheme called PDS. And when you compute the ratio of those two couplings after fitting into data, you find that CT is much less than CS for the nucleon-nucleon system, or if you prefer the neutron-proton system. And in the limit that CT is exactly 0, we have there's a symmetry which is called Wigner's SU4 supermultiplet symmetry, in which we can arrange the spin states of the proton and neutron into a single 4-dimensional vector. So this goes way back to Wigner, and it has many interesting applications and successes in nuclear physics. And there's a multiplicity of explanations for why one would have the Wigner SU4 symmetry starting from QCD. And one explanation is the large N limit. And in the large N limit, you get a different SU4 spin flavor symmetry, which implies the Wigner SU4 symmetry as an accidental symmetry. And that's very nice. And you also get Wigner SU4 symmetry if you assume that Schrodinger's symmetry, that is that the scattering lengths, the singlet and the triplet scattering lengths are near unitarity, that is, they're much larger than a characteristic distance scale. And that's because the Wigner supermultiplet symmetry is depending not on the difference of the scattering lengths, but the difference of the inverse scattering lengths, which of course are very small when the scattering lengths are big. But we see that also if we just assume vanishing entanglement, if we assume that sigma.sigma operator vanishes, then we also get a Wigner SU4 supermultiplet symmetry. So all of these explanations for why we would get CT equal to 0 are the same. So that's interesting, but it's not really very good for our trying to understand whether entanglement is useful, because the entanglement just predicts what other things predict. So then we can go to strange physics. So in strange physics, so if we again look at very, very low energy interactions among neutrons, protons, and the hyperons, so that we can neglect the momentum dependent operators, then instead of having 2 operators, we have 6 operators at leading order. And here are these indices, these I and J indices are spin indices. And so in particular, you see that the spin indices are really entangling in these operators, except for the operator C5, where we have 2 sort of disjoint blocks that don't talk. So all these ones that are underlined all entangle spin. So here the theory expectations are a little bit different. In the large N limit, you get a different SU6 spin flavor symmetry. But now the symmetry doesn't imply that any coefficients vanish. It just implies that the 6 coefficients are related in such a way that they depend only on 2. So the C's depend on A and B. Again, if the scattering lengths are large for all of the channels that we have for the strange baryon scattering, then again we would get C1 through the only C5 would survive. But the vanishing spin entanglement would suggest that all of the operators except C5 would vanish, and that gives an SU16 spin flavor symmetry. So in this case, there really is a unique prediction from vanishing entanglement. Of course, now comparing these predictions to experiments is really very difficult because we don't really have much data for the hyperons. The data we have is really poor. But fortunately, here we can do lattice QCD simulation.
Silas, may I ask a question? So, so here you formulate the so here you studied the entanglement in the spin space. So is it possible to reformulate the argument in the flavor space?
Absolutely, and that's and that's a really good question. I mean, so it's actually very simple to see that in the 2 flavor case. So as I said, we chose a basis in which we expressed the S matrix in terms of the, say sigma 1 dot sigma 2, where sigma are the spin matrices, but we could equivalently have formulated the S matrix in terms of the tau matrices, say tau are the Pauli matrices for isospin. And then in that case, all of the arguments would carry through, except instead of thinking in terms of spin entanglement, we'd be thinking in terms of flavor entanglement, and everything would go through in the same way. Here it's a little bit tricky because we still have 2 spin states for each baryon, but the baryons are in the octet, right? So here the consequences of SU3 of the flavor symmetry will be somewhat different.
Okay.
So I would say that, so in the 2 flavor case, you can look at flavor entanglement and spin entanglement, they're the same. Here in the 3 flavor case, we're really focusing on spin entanglement.
Okay, thank you.
So may I ask a simple question here?
Of course.
And so my question is, if I'm not expert, but it seems to me this action is the tree level action. So suppose I consider the loop effects or the RG effect, could that automatically generate C1, C2, or there's something guaranteed that even in the including the loop effect, C1, C2 are to be to be 0 always?
Yeah. So right. So this is just so here. Well, we're assuming that there's an effective field theory, so that leading order, as you say, would just be given by tree level, and then we can basically just fit these coefficients. And of course, even in this case, if we treat the problem exactly in quantum mechanics, then we have to renormalize the coefficients because these are all delta function interactions. But then what we can do is we can apply these arguments to the renormalized coefficients, which is really the way you should think about it. But as you say, if we want to go to next order in the effective field theory and include momentum dependent operators, then we have these operators get shifted, and then the operators of the next order also have to be renormalized, and they have new low energy coefficients. And so you would have to then redo the analysis at next to leading order and see whether any of these predictions still hold. So I should say in the strange case that hasn't been done. Actually in the original paper on this in the 2 flavor case, the next to leading order analysis was done, and again it seems like entanglement is minimized, but even including next to leading order effects, but it's not as striking as the leading order.
Thank you so much.
Of course. So anyway, so we don't really have experiment to test these predictions. but we can use a lattice gauge theory to do that. And so this was work that was done several years ago by many people, and here are some of the sort of leaders of the analysis. I mean, and these are simulations that are done with pions that are much heavier than the pions of nature. In fact, they're done at the SU3 symmetric point, so where the strange mass is kept more or less at its physical value, and the up and down mass are degenerate or the same as the strange mass. So that's a pion mass of 800 MeV, but in that case, the results are truly striking. That all the coefficients except C5 are consistent with 0. And these uncertainties include statistical and systematic uncertainties for the lattice calculation. The plot on the right is not quite as striking because it's a lighter pion mass, and of course there are less statistics, and therefore larger uncertainties. But the two plots are actually consistent within uncertainties. So the conclusion is that lattice QCD agrees with predictions from vanishing entanglement. And so it seems that we really do get a prediction when we conjecture that for the scattering of strange baryons, minimization of entanglement implies a new SU16 spin flavor symmetry, and that seems to be agree with lattice data. Of course, it's very limited. This is pretty much all we can do at the moment using lattice gauge theory, and even these results have been called into question recently. It's very difficult to get results, experimental or from lattice gauge theory, for the hyperon interactions. So anyway, so we've done sort of hand-waving arguments about what actually entanglement is by just looking at the spin operators that appear, and we really want a real measure of the entanglement of the interaction. And so here we want to think of the baryons themselves as just spin-a-half fermions that are really just correspond to qubits. Which are represented by these little two spheres, and each of these spheres is parameterized by the two spheres. So it has so basically each of the fermions has an angle phi and an angle theta. And for the scattering of the qubits, and again, fermions or baryons or whatever you want, it's very general. Then what you can think of in the initial state of the scattering, you want to take a product state. So you take some, like for instance, as an example here, I show a spin up proton, a spin down neutron, which are states that do not interact and have never interacted with each other. So they're just a tensor product. They're just a product state that has 0 entanglement. But what happens in the scattering process, through the strong nuclear force or through whatever force that you have where they interact, out in the final state, in general, you're going to have a mixed state or a superposition of say a proton and a neutron state with different spins. So we like to characterize the entanglement associated with the scattering process. So here, the first thing I want to do is just re-express the S matrix that, remember, we wrote down for the low energy nucleon-nucleon or fermion-fermion scattering in terms of the unit operator and the sigma piece. And here, I'm instead writing in a somewhat different basis for reasons that'll become clear. And so now the S matrix has two parts. It has a unit operator, and then it has this P12 operator, which is it's a well-known operator in quantum information. It's the swap operator. So it takes that initial state of the proton and neutron with a spin up and spin down, and it just flips the spin. So in particular, it takes a one product state, so the initial product state, to the product state that you get by just flipping the spins, neither of which have any entanglement. So then we would guess that a measure of the spin entanglement would be a product of the coefficients of the unit operator and the swap operator. Because if either U or V are 0, we should get 0 entanglement. And we take the absolute value because we want the object to be real. So then we find that the spin entanglement scales is the sign of the difference of the singlet and the triplet phase shifts, again representing spins aligned or anti-aligned. That's perfectly consistent with what we found for instance, for the Wigner symmetry. So when the spin singlet and the spin triplet are equal, then you have vanishing entanglement. So this can be done in a fairly general way by defining a so-called entanglement power. And you can do it in a way that's independent of the state by just assuming that the initial states in the scattering process live on the two spheres. So each of them are actual qubits that depend on each depend on their own phi and theta angle. And so then we can define an entanglement power, which is the average over the elements of solid angle associated with each of those qubits. And then we have to take the trace of a reduced density matrix. Again, the S matrix takes the in state to the out state. We can define the density matrix, and then we can trace over one of the spins to get a reduced density matrix. And so in terms of the Renyi, the very general Renyi entropy, this is related to the exponential of the second Renyi entropy. And this gives a completely non-unique, but a very useful measure of entanglement in the scattering process. And so here it is. So this is what it actually is when you do that calculation. This normalization ends up P really just depends on how you want to orient the spins in the initial state. And it takes so for this particular it takes a numerical value which has a certain bound. It's bounded to be less than 1. And then what I plotted is this entanglement power versus center of mass momentum for the nucleon-nucleon, the neutron-proton phase shifts, and I've just taken the curve from data. So these are just different nucleon-nucleon potentials, which you can think of a representation of the experimental data. And so you get you this sort of interesting curves.
So why P? So why the momentum here can go beyond the pion mass? I mean, in your previous discussion, it seems that you assumed the pionless EFT as a starting point.
Excellent question. Right. So here I'm just so here I'm plotting basically the experimental data. I mean, so these are these curves are basically experimental data. And you in fact you can think of the split between the different curves as in some sense a measure of the experimental uncertainty. And so of course the experimental data goes way up to right to pion production threshold. So actually to inelastic threshold. And so I'm just showing the data way up there, but you're absolutely right that for the pionless theory, we are constrained to be at momentum certainly less than 100 MeV, right? I mean the pion mass is 140 MeV. So clearly the pion-less theory is not applicable up, past this second maximum of the curve.
Okay, thank you.
Yeah, so this is an excellent question. I mean, this is just sort of showing the data, and it's just sort of interesting. I mean, this is the measure of the entanglement in the scattering process. This is what the data tells you, and it's interesting because you have you start at 0 entanglement, and then you have a second 0. There's a maximum of the entanglement and a second 0. And of course that second 0 is just when the S matrix becomes proportional to the swap operator. And that actually that occurs at a center of mass momentum of like 19 MeV. And nothing interesting is happening in the nucleon-nucleon phase shifts at 19 MeV, but in this plot something interesting is happening because that's exactly where the sort of entangled state then just for at one point of momentum becomes a product state where there's no entanglement. So anyway, so that is the measure of entanglement, and this curve is what it is, and part of the motivation for trying to think about the S matrix in a different way is to try to get some sort of understanding for the momentum independence of this curve. Again, the results we showed for the Wigner SU4 symmetry and this new SU16 spin flavor symmetry in the SU3 case are really statements about the entanglement power very close to the 0 point here, where we're just including momentum independent operators. So we can go back to the question we sort of asked at the beginning: do measures of entanglement provide interesting new information about scattering processes? And the answer is that at threshold, the minimization of the entanglement power recovers this Wigner SU4 symmetry, which is nice. And in the 3 flavor case, we seem to get an actual new prediction which agrees with lattice data. and it implies this SU16 spin flavor symmetry, which would imply that a leading order and now in this SU16 invariant effective field theory, we just have basically one operator where the baryons are in this 16-dimensional representation, the fundamental. But of course, and this is a nice prediction, but to actually test this beyond what we've done is something that's for distant future lattice QCD simulations, I would say. So then beyond thresholds, as I mentioned, you can do the next order in the effective field theory in the two-flavor case, and you see that entanglement continues to be minimized, but not in as dramatic a way. And as I mentioned, the structure of the momentum dependence of this entanglement power is mysterious. And so since the effective field theory description really relies on the locality of the space-time description, then we ask this question: is it possible to obtain the S matrix from a space-time independent geometric formulation? And the answer is yes. So before we go on to this geometric formulation, I just want to mention a couple of S matrix basics that most of you probably know very well, but just to get some sort of common language. So in single channel S wave scattering, so S is just a phase. And of course, we have the phase shift, which is just a momentum dependent object. And here K is the center of mass momentum. And so this is then related to the T matrix or the scattering matrix up to some arbitrary normalization coefficient that here is just fixed to match onto the Feynman diagram expansion in the EFT. Then very near threshold, the scattering length dominates. And so here I've just written the scattering amplitude in terms of the effective range expansion. And what you notice is something very interesting, and there are two fixed points of the renormalization group here. One is the trivial one in which the scattering length vanishes, and there the scattering amplitude, of course, vanishes. And then the other one is the unitary fixed point. And at the unitary fixed point, the scattering amplitude is just some complicated, not complicated, but it's just some not very enlightening function of momentum, which satisfies the Schrodinger symmetry, the non-relativistic conformal symmetry ward identities. But the S matrix, you see, it looks very different. It's much more symmetric than the T matrix. And the trivial and unitary fixed points are actually just the plus and minus one values of the S matrix. So the trivial point is when A is 0 or near 0, S is near 1 or 1. And at unitarity, when A goes to either plus or minus infinity, S goes to minus 1. You also see that S has symmetries that T doesn't possess, and that's basically because you see that S is a function of AK, whereas T is not. So in particular, you can rescale simultaneously the momentum and the scattering length, and in a way that leaves the S matrix invariant. And then that tells you that you can, to get to unitarity, you can either hold the momentum fixed and take A to infinity, or you can hold the scattering length fixed and take K to infinity. And of special importance is another symmetry that, or interesting transformation that the S matrix has, and has a UVIR symmetry that inverts the momentum, particularly under K goes to 1 over A squared K, S goes to minus S star. And so under this transformation, the single channel S matrix maps to minus its complex conjugate. And in particular, that means that this UVIR symmetry maps the trivial fixed point to of +1 to the unitary fixed point -1. So in some sense, it is kind of like a weak, strong coupling symmetry. This symmetry is quite odd because it really has nothing to do with the Schrodinger symmetry or non-relativistic conformal symmetry, which you have at the fixed points. It's really a symmetry that's actually beyond that. And that makes it very hard to understand this symmetry from the point of view of an action as a space-time symmetry. But it nevertheless is a symmetry, and in particular, it's an actual symmetry of the S matrix in the two-channel case that we're really interested in. I'll just mention briefly that even though this symmetry, this UVIR symmetry, doesn't show up as a space-time symmetry in the action, it actually is a symmetry of the RG flow of the coupling constants. So in the effective field theory, we can define a renormalized coupling constant using a cutoff scheme or dimensional regularization with PDS. And here omega is the RG, the running RG scale. So the S matrix is independent of omega. So that's the running coupling. And the beta function associated with a coupling exhibits the two RG fixed points. There's one, so there's the unitary fixed point when C0 hat is 1, and then when C0 is 0 is the trivial fixed point. And what you see is that under a UVIR inversion of the renormalization scale, what you do is it just maps the trivial fixed point into the unitary fixed point. So that's just really just a little bit of an aside, because this UVIR symmetry will be important for what follows.
And Silas, can you go back to your previous slide? So here, when I read your paper, the previous one, I mean,
sure.
So when I read your paper, I found that if you allow K to go beyond the physical region, for example, allow K to take the negative value, and you take K to minus 1 over a squared times K. There's also a similar result. So under that map, the scattering amplitude also mapped to another quite similar scattering amplitude. And of course, by doing so, you lost the interpretation of UV and the IR interchange, but it's at least formally you still have a similar operation.
Yeah, absolutely. This is a really good point. So if you look at the general transformation here, so this is just one special case of a general transformation, which is really a Mobius transformation. So the general form of the transformation is K goes to, if you want, AK plus B over CK plus D. You know, it's a kind of Mobius transformation.
Yes.
And as you say, you can choose those values so that you can have a transformation K to minus 1 over K. And the general Mobius transformation includes, in addition to an inversion, a kind of translation. And if you keep K to be a real parameter, so K just spans the entire real line, then in general, this Mobius transformation is a mapping of the real line to itself. So that in general, that includes as a if you will as a kind of subgroup a UVIR transformation, but it also just includes translations along the line, and also transformations that take you from the the right half, from the positive line to the negative line, and so on.
Okay.
So it's just one. So this is just one sort of subgroup of a larger group of transformations that's obeyed by the S matrix.
Another question is that in your paper, you assume that the arguments are made on the assumption that the energy is below the inelastic threshold. So my question is, suppose you do the analysis for an optical potential, or you do the analysis for the n bar n scattering, where there is an annihilation channel. So in that case, you will have the complex low energy constants. My question is, does the formalism also holds when you allow the phase shift to be complex valued? So you just allow the phase shift to be complex valued, and it seemed to me that the formalism will also hold there, although in that case, the A will be a complex value, a valued number.
That's right. So I mean, here I'm sort of assuming, at least so far, I mean, I'm assuming that I've pushed, basically all short distance physics in some sense to infinity, right? So the both new threshold for new particles, like in nucleon you'd have pion production threshold. So I'm pushing basically the pion mass to infinity, so that all short distance physics and all inelastic thresholds basically are accumulating at k equals infinity.
Okay.
And then I sort of neglect them. But yeah, so you're absolutely right. So for anything interesting, we have inelastic thresholds, and in the geometric picture, in some sense, the most interesting part of the geometric picture is when you allow the inelastic processes to take place.
Okay.
Which hopefully I'll have time to get to. I'm not sure.
Okay. Okay.
But yeah, I mean, but it's absolutely essential. I mean, here we're really just assuming that all of the inelastic stuff and all short distance physics is just pushed away to infinity. But then, of course, we want to bring it back.
Okay.
Okay. I'm again frozen. Let me see. Oop. There you go. Okay, so now on to the geometry of the S matrix. So now back to NN scattering, or if you will, neutron-proton scattering, in which we really have two channels, right? We have the singlet and the triplet channel. And now in this case, instead of having just the two RG fixed points, where S is plus or minus 1 as in the single channel, we actually have 4 RG fixed points. And that's because we have now two scattering lengths, A0 and A1, corresponding to singlet and triplet. And they can both be 0. They can both be at unitarity or infinite, or we can have 1, 0 and 1 infinite, and vice versa. And so that's 4 fixed points, which written in terms of the S matrix, we write in terms of these S1 through S4. So this has a sort of interesting symmetry properties. Now, if we look at leading order in the effective range expansion, then we have our S matrix, which remember is written in terms of the unit operator times U plus the swap operator times V. Then this is the form that the S matrix takes at leading order in the effective range expansion and leading order in the effective field theory. It just depends on the scattering lanes. So we can then formulate some useful coordinates for an embedding. So we want to now think of the S matrix as represented by a set of constrained coordinates. So now U and V are complex coordinates, and we can write them in terms of the real coordinates X, Y, Z, and W. And then in terms of X, Y, Z, and W, then unitarity of the S matrix implies two constraints. One, that X, Y, Z, and W parameterize the 3-sphere, which is just that first equation in the box. And then there's in addition this projective constraint that's basically a plane, and it's really the intersection of a plane with the 3-sphere, which gives us the surface we want. And the parametric representation of that can be just written as follows in terms of these angles phi and theta. And it's really important. I mean, these phi and theta are just the singlet and triplet phase shifts, but multiplied by a factor of 2 so that we can periodically identify them so that we can have phi and theta each in the interval 0 to 2 pi. And that gives that then phi and theta then form a sort of toroidal two-dimensional surface. And here we've set R equal to 1 here. So R equal to 1, going back to the previous question, corresponds to really assuming that the processes are entirely elastic. If we allowed R to deviate from 1, then of course we would see, and of course it can only be less than 1, then we would see deviations of away from unitarity violations due to inelasticities. So then embedding these coordinates in the 4-dimensional Euclidean space, then what we find is just a very simple compact Riemannian manifold, which is given by this metric ds squared in the box. And it's sort of obvious that that's what it had to be. It's just there are only 2 degrees of freedom that describe the S matrix. It's the 2 phase shifts, delta 0 and delta 1, which is just equal to these phi and theta angles up to a factor of 2. And so here, this metric really defines what's called, it's a 2-dimensional Euclidean surface, but it's really a flat torus, which means that it's a 2-dimensional surface, but we have the ends of the square formed by the 2 sides with phi and theta are identified periodically. so then if we think of of how the fixed points of the renormalization group, and so again, so these are the points at which you really have a conformal field theory. So either the scattering lengths vanish or infinite. And so in this square, then these are the S1, S2, S3, and S4. And I've added other mirror fixed points because again, the flat torus, you can think of extending in infinite direction in all directions, where you would just have mirror representations of the fixed points. Everything that doesn't entangle is in blue. And so the blue lines that are connecting horizontally these fixed points, these are just the Wigner SU4 points. So these are the points at which the singlet and the triplet phase shifts are equal. It has a rather complicated isometry group. The very important thing here is that if the entanglement power in the scattering process vanishes, then there's actually no manifold. There really is no flat torus. There's just a two-dimensional surface, which is really just a lattice of fixed points as vertices. And then we have the special geodesics, straight lines that can move only in the direction shown between the fixed points. It's only when we allow the entanglement power to turn on that trajectories in this space can sample the entire continuous space, and therefore there's an actual manifold. So here, something that sort of looks complicated is actually very simple. The trajectories on a Riemannian manifold are governed by the following action, which we're all familiar with, where I've just added a potential term. So this is just the familiar action that when you vary it, you get the geodesic equation. Here, the variable chi is just can be either phi or theta, describing the two-dimensional surface. And I've added the v. So if you set v equal to 0, then this is just a geodesic equation for trajectories that move on this flat torus. This kappa is just the usual inaffinity. If we want to consider affine parametrizations of the curves that we have on the manifold, then we can set kappa equal to 0. But we'll see that we actually need inaffine parametrizations because we want to our parameter sigma that will parameterize the curves is this going to be the momentum, in particular for our choice, the center of mass momentum.
And so how to determine n? So here you have n. How to determine that?
Well, that's right. So well, first we have to, we can choose an affine parametrization for the curve, but say it's some parameter lambda. So in that case, n will be fixed by the affine parametrization, but the parameter lambda, it'll describe a trajectory on the flat torus, but lambda will have nothing to do with momentum. So if we want sigma to really be the momentum, then kappa has to be non-zero, and then we need an additional constraint in order to fix both n and v. But we can fit them from the data, and I'll show you that in just a minute.
Okay.
Anyway, so on the flat torus, the chi are just these two coordinates phi and theta, and it's just a trivial Euclidean, two-dimensional Euclidean metric.
Can I ask a short question just to be sure?
Of course.
And so for this action, do you need to impose in the diffeomorphism symmetry? If so, what does that corresponding to any symmetry in the original theory?
Yeah, here we're not. I mean, it's just a completely general. So setting v equal to 0 is just basically geodesic on the two-dimensional plane, and so then there's some associated symmetries, some killing vectors that you can construct, which are related to those isometries I showed on the previous slide. And so, but as we'll see, we for special cases, when we put in v, if we require certain symmetries to be satisfied, then the problem becomes exactly solvable. So I'm not sure if that answers your question, but let me maybe get to that point and then maybe ask again if it's not clear.
Okay, thank you.
So anyway, so here what I've shown is actually this dash curve, which you should focus on first. So this is actually experimental data. So that's just the Nijmegen partial wave analysis. So it's one of the representations of nucleon data. And so you see that that it starts at this trivial fixed point S1. It's particularly the mirror trivial fixed point. And then what it does is it moves along the solid red curve, but then it deviates from the solid red curve. Then it goes and it basically where the curve ends, it basically hits inelastic threshold. It's a momentum, center mass momentum of like 400 MeV or something. You see that the solid red curve, on the other hand, so that's just the solid red curve is just leading order in the effective field theory, or if you want the scattering length approximation. So we're just saying that the S matrix is given by determined exactly by the two scattering lanes A0 and A1, is shown in these equations for phi and theta. So it's written in terms of inverse tangent, but it's this is just a different way of writing the effective range expansion where we just keep the scattering length. And the thing to notice here about this curve is that it has a symmetry about phi equals theta. It has a reflection symmetry about this diamond that you have there in the middle. And of course, it's not surprising that the data follows the solid line, but then at a certain point, effective range corrections, which are clearly there, kick in, and the data deviates from leading order, which is just represented by the scattering lanes. And so what is that symmetry? Well, that symmetry is just the UVIR symmetry that we had that we looked at in the single channel case, except now it's a generalization of that to the case with two scattering lanes. So it's just an inversion of the momentum. So under an inversion of the momentum, you have this symmetry that leaves combinations of these angles, theta and phi, invariant, and therefore it's a conformal invariance, because a conformal invariance by definition is a symmetry that leaves angles invariant. And the remarkable thing is that now, going back to this geodesic equation with a potential, we previously had we had too many unknowns, and so we could fit the potential to the data if we wanted. But in this case where we have the conformal invariance, or this UVIR symmetry, we can actually solve for the infinity, so for this n, as somebody asked, and for explicitly for the potential, which gives the leading order and the effective range expansion. And it's just written in the box that it's just the system is completely integrable, completely solvable. And that is the potential. And the potential is just this harmonic function of linear combinations of the angles. This epsilon, for this case, the epsilon is equal to -1. So we can look at equipotential surfaces, and so if we look at this the trajectory, then the dark regions are the regions with the no potential, and the bright regions are the regions where the potential is strongest. And you see that what's happening is that the potential is you can think of it as a kind of repulsive potential, which is pushing deforming if you will, the geodesic, which would just be the straight line trajectory, away from being a geodesic to being an actual curve on the manifold. And then particularly interesting is the equi-entanglement surfaces. So here, again, the blue line is the SU4 Wigner symmetry, or phi equals theta region where there's a zero entanglement. And so now we can go back to the plot of the entanglement power as a function of the momentum, and we can now sort of see what is happening in this geometric model. So as the trajectory on the flat torus starts on the the top left corner of the flat torus, so you see that it goes into a maximum, then it hits the minimum, and then it hits the maximum, and it hits a minimum, and it's just giving exactly the behavior that we see for the entanglement power. But of course, the entanglement power is just it's kind of squeezed relative to the curve on the flat torus. So it just gives you a sort of an alternate understanding of what this entanglement power is. It doesn't. So far, it's just sort of it's a cute piece of mathematics, but it gives some new insight, but with marginal returns. Okay, I'm quickly running out of time. So let me just say that one can also look at causality, how causality bounds appear on the flat torus. So even though the scattering is non-relativistic, it still has causality constraints. And of course, there's no light cone, but we still expect that for instance, scattering proceeds. The scatter wave doesn't get has to be scattered in a causal manner. And in non-relativistic scattering, these causal bounds are sometimes called Wigner bounds, which are usually expressed as constraints on the effective range. And so now we have to think of more complicated trajectories that involve not just the scattering length approximation, but also including effective range and higher. And what you find is that these Wigner bounds just translate into geometrical constraints on the phi and theta coordinates on the flat torus. And so looking in the left torus, then you see that basically you're divided into quadrants, and these constraints, the Wigner bound constraints that are given at the bottom, these inequalities, basically tell you the directions in which the trajectories can move. And so you see that the one in the top right corner can go in any direction, and so that's a perfectly causal trajectory. But the bottom one, well, we have the purple one in the dotted line. That's just the scattering length approximation. The effective range there is 0, and so there's no causal bound. But the other one is actually forbidden by causality, because you can see from the arrows, the causality only allows it to move either up or diagonally up or sideways to the right. And so as soon as it starts to bend around, it actually violates causality. There are other causal constraints that have to do with when a trajectory exits one side of the flat torus and enters another, it can only do so in certain directed ways. So finally, to inelasticity, and we'll see that it somehow then touches on holography. We now want to think about allowing inelastic loss, is what was asked before. So that would be like adding a complex piece to the Hamiltonian, if you want, or a complex scattering length. In the nucleon-nucleon system, that could occur from pion production, but it can also just occur through the interaction of the system with the environment in some way, so that there's a loss of unitarity. So here, sort of crucial assumption is to assume that the violation of unitarity occurs in a way that's consistent with the Wigner SU4 symmetry, so that the inelasticity parameter, which I'll call here eta, is the same for the singlet and the triplet. So now we're allowing basically this R parameter to actually be a function. It can actually be a function of R, not just R. And for R equal 1, we recover unitarity, but for R less than 1, we can violate unitarity. And we can again do the embedding into the 4-dimensional Euclidean space, and now we find a much more interesting metric. So we now find a metric which is actually a hyperbolic space that has a negative curvature and an associated Einstein tensor. And looking at that metric, what you see is that for a fixed value of R, so for like R is equal to 1, then you just have a flat torus. But now for each value of R, you have a separate flat torus. And what you see is that there's actually a singularity. You see that the scalar curvature as it goes 1 over R squared, and there's a singularity at the point at which you have the maximal violation of unitarity. Remember, R is less than or equal to 1, but basically at R equals 0, you've just saturated the bound, and you can't violate any more unitarity any more than you have. So here, the generalization of the trajectory equations for this hyperbolic space with a non-vanishing curvature are just given there. Then you can ask questions whether you can engineer a bulk potential which will reproduce the leading order and the effective range expansion while allowing for inelastic lossiness. And it turns out you can do this. And what you find is the generalization of the potential for the case when you have the conformal symmetry on the boundary just acquires this additional 1/r² factor. And then you can solve the system. And I've sort of run out of time, so I'm not going to go through this unless the people ask questions. But I'm just going to show sort of a figure of what this represents. So I'm now representing this bulk space which is really a hyperbolic space by a sphere, which is of course not the best way to represent it, but anyway, visually it's nice. And so we see is that roughly the surface of this sphere you can think of as the flat torus, where you have these fixed points, S1, S2, S3, and S4, and so on. And as long as we're on the surface of the sphere, we're satisfying unitarity exactly. And so in particular, the trajectory that we've been considering is between the trivial fixed point S1 and the unitary fixed point S2. But we can allow violation of unitarity, and as soon as we leave the trivial fixed point and unitarity is violated, then we burrow into the bulk of this hyperbolic space. And we can come back out to the other fixed point S2, but we can't quite get there. So we can reproduce, we can recover this trajectory, which is just again leading order in the effective range expansion, but only up to an uncertainty. So again, compared to the usual holographic duality, you have a conformal field theory on the boundary, and then you have a theory with non-trivial curvature in the bulk. But here, there's no real conformal theory on the boundary. It's just the boundary is just unitary evolution of the S matrix, and the bulk just corresponds to various kinds of inelastic loss and violations of unitarity.
So Silas, I think in high energy physics, when people talk about holography, they mean that the boundary theory are totally equivalent to the bulk theory, and you can learn the bulk theory by studying the boundary theory, and or you can learn the boundary theory by studying the bulk theory. So my question here is, so here the boundary, the boundary is elastic theory, and the bulk is an inelastic theory. So do you mean that when we can learn the bulk by studying the boundary?
That's right. So yeah. So here I looked at so usually in the usual correspondence, you're sort of you go into the bulk theory, but then you really look at the limit where the bulk, so that you're really on the boundary, and you formulate a kind of dictionary, and so no such dictionary has been formulated here, because the system is, there aren't really any kind of correlation functions or anything. So there's nothing to formulate a dictionary for. I mean, the only thing we really have is kind of this phase, this S matrix, that just moves between fixed points on the boundary. And so this trajectory which burrows into the bulk, you want to think of it as a kind of way of thinking about error correction. So you can, so if you do have some, for instance, inelastic loss to the environment, so you can think of that as analogous to loss of coherence, right, due to the interaction of the environment. Then can you recover the trajectory that you actually want, which is the one that's unitary and on the boundary.
Okay.
And this is just an example of just showing that you can't quite get there, that you can only do it up to a certain error.
Okay.
But the question you ask is, it's an interesting one, is whether somehow there are other observables here that are being missed, in which where you could formulate some sort of exact correspondence.
Okay, thank you.
Okay, so that's it. So I just want to summarize. So in some sense, the main physics point to take away is this first bullet. So that in baryon-baryon scattering, the minimization of the entanglement power implies some new symmetries in the strange sector, which really simplify the effective field theory. It implies this SU16 spin flavor symmetry, and lattice QCD simulations seem to agree with these predictions. But of course, we would like to see other applications of this prediction of this effective field theory. It's just hard to do that because there's so few observables that are accessible via lattice QCD simulations. And so again, the takeaway from this bullet is really that entanglement does constrain scattering, and it would be interesting to find other systems. And in particular, going to the last bullet, you can think of other obvious examples in QCD physics, like looking at pion-pion or pion-nucleon scattering, and it's a little bit different because you have, instead of qubit scattering, you have qubit or qubit scattering. But for those cases, what one finds is that the consequences of entanglement minimization are really pretty indistinguishable from large N QCD implication. And part of the problem is that in those cases you have pions on external lines, and pions are Goldstone bosons whose interactions vanish for very low energies. So in a sense, you're looking for an effect of vanishing entanglement on top of a very, very significant effect, which is the vanishing of the pion interaction at low momentum. But it would be interesting to try to find other examples of scattering where entanglement is minimized. And so for the middle bullet, then we've seen that in an attempt to sort of understand this entanglement power, this measure of entanglement in the scattering, it sort of leads rather naturally to this geometric formulation, in which the S matrix is just a trajectory that propagates in this in a theory space, which is really only exists with the quantum entanglement, and is really bounded by unitarity. And then it gives this this rather simple toy model of holography when you allow inelastic loss. And it would just be interesting to understand the symmetries that you have for this system, particularly this UVIR symmetries in the context of the Schrodinger symmetry, which is the non-relativistic conformal invariance that you have a unitarity. But so far, it's really hard to make progress on that. Okay, thank you.
Okay, thank you. So is there any questions?
Oh, hi, Silas.
Hi.
Hi. So I have a question related to the MP scattering. So as you mentioned that you can demonstrate in the S wave, we can observe the entanglement in the MP scattering, but can you also observe something similar in higher partial waves?
Yeah, it's a good question. We just, the only thing analysis that's been done is, if you well, I should say, I mean, I guess it really, I'm trying to think of whether it's been done for the higher partial waves. The problem is, of course, the higher partial waves are sort of sampling larger momenta. And then, as soon as you go to larger momenta, then the system becomes a little bit messier. And so, I think, as I mentioned, for the nucleon system, we've taken an analysis which we're up to next to leading order in the expansion, which involves quite a few low energy constants that are fit to the data. We analyze what whether the operators that naively don't entangle or really dominate over those that do entangle, and it seems like the basic patterns are satisfied, but yeah, I think that I mean, I would just say that this hasn't been studied in enough detail.
Okay, and does it require
it's an interesting question.
I mean, does it require the low energy constant to be fine-tuned, or just natural size?
Well, yeah. So in a sense, yes. So in a sense, the question is whether, you know, if you have the effective field theory, for instance, say you're looking at a particular P wave channel, and then there'll be some sequence of operators, right? So if you work down a load, there'll be some number of operators that describe that physical system experimentally, right? And you can fit the coefficients of those operators. And then in some sense, the question you're asking is are there, you know, first of all, you know, do the operators that entangle, are they somehow minimized? And that's sort of similar to asking the question, are there coefficients of operators that are anomalously small, so unnatural size? And so in some sense, that's the goal, the motivation in some sense of thinking about entanglement is that in nucleon scattering, and also in baryon scattering and many scattering processes, when you fit the low energy constants, you find that sometimes low energy constants are just really anomalously small. And there's no obvious reason based on the usual symmetries as to why they're small. And the question would be, could something like entanglement or other measures that maybe we haven't thought of yet explain this smallness?
I see. Okay. Yep. Thank you.
Of course.
Is there any other questions? Silas, I have two questions. The first question is that as we all know that the analytic properties of S matrix plays an important role in analyzing scattering. And my question is it possible to generalize the geometric picture to study, to rewrite the analytic properties of scattering in the geometric language? Is it possible to do that? Since then you can study, for example, the bound state or the resonance states in the geometric language.
Yeah, I mean, it's a really good question. I mean, here, so first of all, there's the you know, sort of everything we've done is in this non-relativistic limit, which really simplifies, of course, the you know, the situation. And here, and we really focus on the scattering states. I mean, really the momentum here really, I mean, we do have bound states which live in the complex momentum plane, at least in one half of plane. And so some of the issues I discussed related to causality touch on this, on the issue of you know, thinking about the analytic S matrix and its properties, and how causality shows up as sort of analytic properties of the S matrix. So I think there's been a little bit of exploration of that, but I think there's more to explore there. And I think the real interesting thing is whether one could generalize this geometric picture to some relativistic system, because there the whole framework of the analytic S matrix is just much more powerful.
I see.
Because like in scattering, you know, you have crossing symmetry, and you have just a much more powerful formalism. But the problem is that like in pi scattering, since the pions don't have any spin, they just have isospin. It's really hard to formulate any interesting geometric picture for pi scattering. You kind of need both non-trivial spin and non-trivial flavor in order to get something interesting. And unfortunately, we just don't have that kind of system at our disposal in nature. I mean, we can invent sort of fictitious systems and analyze them, but it's significantly more difficult.
Okay. So my second question, I think, is a more general question. I mean, have you thought of how to generalize the geometric picture to the n-body scattering. I mean, so in the two-body scattering, you have a manifold and also the word line. I mean the scattering corresponding the physical scattering corresponding to a word line in a manifold. So, and in the two-body scattering, you only have one kinematic variable, that is the momentum p. And when you do the analysis for the n-body scattering, I think there are more kinematic variables, and if the geometric picture also applies there, I think maybe maybe that corresponds to the, I think the classical theory of string or the brain action. So have you thought of that questions? So how to generalize the geometric picture to the n-body scattering?
You know, I've thought about it quite a bit, but I've made no progress. I mean, that's the comments you make about the string. It's actually very interesting. To me, a problem that sort of interests me a lot is the problem of fermions, a Fermi gas at unitarity. So generalizing from, you know, say a system of 2 neutrons to n neutrons, and being able to take the thermodynamic limit. So in that context, I've tried to think of ways to generalize this to the n-body system, with a hope that it could give some sort of analytical understanding of that system, which is, you know, very, very difficult. I mean, basically, you know, has to be solved numerically because there's no obvious small parameter. And so yeah, so actually, to me, that is in some sense one of the most interesting questions, is how one would generalize, even to generalize to the 3-body or 4-body system, would be interesting. But, you know, even going to the 3-body system is quite challenging.
Okay, thank you very much. So is there any other questions? Since there's no questions, let's thank Silas again, and thanks very much for your talk, and we learn a lot from it. Thanks.
Thank you very much. Thank you for having me.
Okay.
Take care.
Okay, bye.
Bye.
Okay, I will close the meeting room now. Bye bye.
Take care. Thank you. Bye bye.